All right. First and foremost, I know you all have waited for this moment for a long time. Here is the distribution of grades for the midterm exam. So, actually pretty good. I mean, the average is what, 81, median 83, a min of 31, and max of 99. Well, I'll email you. We just finished grading today, so I'll email you all your grades after class sometime today. And then if you want to see your actual exam, come to office hours to visit me or a TA. We'll be happy to go through your exam, show you what you got right, didn't get right, all of that. Questions? Cool. All right. I don't really like this orientation, but I don't know, is this good or bad? Usually it's supposed to be more of like a curve.
The slope.
Yeah, I don't, it's just this jump or something, or a ramp, I don't know. I'm not really sure what to think about it, but you know, I mean, I think it means you studied, so that's good, or some of you at least. All right, you can let me know your thoughts later. All right, because today we are going to cover overflows. So now we're going to get to memory corruption vulnerabilities. So this, we're going to crank. I think we have 130 slides or something to cover. It's mainly just used to scare you. There's not, a lot of it is animation. There's not actually 130 or 140 pages of text. Okay, so the important thing to think about is what all this stems from, and all of these vulnerabilities we've talked about all stem from essentially programmers making mistakes and writing what we've looked at C code. So how are arrays done in C? Yeah.
They're like a fixed bit of memory that's set aside for an array.
So a fixed size of memory, how do you specify the size of the memory? Yeah, by hard coding it as you write bracket, the size of however many integers or characters or whatever the data type is. That says you want an array of that fixed type. And what prevents you from writing, let's say, creating an array of 50 characters and writing 100 characters into that array? Nothing. So how do you have to do it if you're doing this correctly? You have to know the size, and you have to pass the size constantly with the array itself, right? You have to have either the pointer to the memory and then the size so that you never go over the allocated memory. Even using something like dynamic allocation on the heap with something like malloc, you still have to specify exactly how much memory you need, and then you need to pass that information down so that everyone else that operates on that array knows exactly how many elements are in it. Why don't you need to do this for something like Java?
Java runs in a virtual environment.
Runs in a virtual environment, so
It keeps track for you.
it keeps track for you, yeah. So the part of the language itself says, you tell me what's an array, I will keep track of the size, and every time you read or write to that array, I will check the size to make sure you're not writing over the bounds. What's the benefit of that? Yeah, the programmer doesn't have to worry about it. They don't have to worry about passing the bounds. What's the downside of that? Speed is the main one, right? Because now every memory access needs to check whether it's in the bounds or not. So essentially, and this is what we'll see, is this lack of built-in boundary checkings in arrays. It causes one of the most common mistakes in C or C++ applications, and we'll see how this can be used for vulnerabilities. So overflows, so what we're talking about here are buffer overflows. So buffer, array, same general concept. You're creating some memory, and by overflowing that buffer, where essentially the attacker is able to write more data than can fit into that buffer. Can do all kinds of cool stuff. We'll go over how you can modify the control flow of the application. You can also modify the data of the application. Exactly how you do this, and this is one of these types of vulnerabilities where your exploit needs to be very precise. It needs to depend exactly on the architecture of the system, the operating system version, all these types of things. There are tools that actually will try to automate this process. We won't get into them here. But essentially, And a lot of things have been done to try to prevent the exploitation of these vulnerabilities, but attackers have gotten a lot better over the years. So every time a new mitigation strategy is deployed, attackers find a new way around that. So, okay, but it all starts with the stack. So what is a stack generally? Yeah, in the back. Correct. So is technically the stack we're talking about here, is that at a high level, what's the data structure of a stack like? Yeah.
Last in, first out. So the last thing you put in is the first thing that pops up.
Yeah, so last in, first out. So you push things onto the stack, and as you pop them off, they go in reverse order. So you can think of you just push an item, 1 item, 2, 3, 4, 5, 6, and then 6 comes off first when you pop, and then 5, and then 4, all the way that way. So, and the way the stack is used in almost all operating systems, or on, I don't know if operating system is the correct term, but on almost all architectures use the scratch as some form of scratch memory for functions. So we're not going to get into we'll get into some of the details, but if you think about it at a high level, how can you have a function call itself? So you've written a recursive function, how can it call itself? Where does that where did the memory for the local variables go? Right? You need to have a new piece of memory for every invocation of a function. So if you have a function call itself 100 times, there needs to be some space in the memory of your program for those 100 different calls that each have different local variables so they don't stomp on each other. So this is all done using the stack. What we will be looking at, all the stacks we will be looking at, start at high memory and grows down. So when we say pushing things on the stack moves the stack down towards lower memory, popping things off makes the stack move up towards higher memory. Is that, well, okay, I'll answer my question. It's essentially an arbitrary distinction, right? It's just, you're talking about how the memory moves. So you could flip it up, you could have the stack grow from the bottom to the top, from high memory to low memory. You could do it left to right, although that's definitely wrong. But as long as we're consistent, we'll always know exactly what we're talking about. And as a function executes, it can feel free to store values onto the stack, pop values off the stack. And some assembly languages, specifically like x86 that we've been looking at, actively support this feature. So specifically the register ESP holds the address of the top of the stack. So what does that mean is inside the register ESP?
Most recent thing put on the stack?
No, not the most recent thing put on the stack. Very close.
A pointer?
It's a point. So what does a pointer mean?
It's you hold the memory address.
Yeah, the memory address of the place that it last put a thing on the stack. Yes. So, and that's exactly why I want to make this distinction, right? When we say it points to the top of the stack, that means it literally has the memory address. So if the top of the stack is at 08, 04, 24 AB, that hex value will be inside the ESP register. Cool. And we have basically two operations onto the stack, pushing things on and popping things off. So a push instruction, push EAX, says decrement the stack pointer. So we're pushing, we're decrementing, we're going down towards lower value memory. Decrement the stack pointer, then put the value that's inside EAX onto the stack in the location pointed to by the stack pointer. So we move it down, put EAX there, and we're done. And then pop is literally just the reverse. So pop EAX says take whatever ESP points to at that memory address, put that value inside EAX, and then increment the stack pointer. How much do we have to increment or decrement the stack pointer here?
But the size of a pointer, the size of the memory address?
So the size of the memory address, which is what? Or
Is it 32 bits?
yeah, 32 bits. It's technically also the size of the memory address, but it's the size of the register, right? So if we're storing whatever's in EAX onto the stack, we need to store 32 bits there, 4 bytes, so we need to increment and decrement the stack pointer by 4. Cool. Let's look at a very simple example. Here, again, we have the stack at high numbers to low numbers. We have something at the stack. So let's say the stack currently points here. Let's say this memory location is at 10,000 in hex. Does it matter exactly where the stack is? No, it doesn't really matter for these purposes, but if I'm saying that the stack points to the value 10,000 hex, then what must be true about the registers? Yeah. Yes, exactly. The value inside ESP must be 10,000 hex, right? Those things are linked. Okay, cool. Other important thing about the stack. So what do I know about values above this number? So what can I say about memory that's above this stack?
It's part of the stack.
It is part of the stack, right? Do we know what those values are?
No.
No, we don't necessarily know. It may depend on runtime. It could be any crazy thing. But why do we know that those are in use or as part of the stack?
Because it goes down.
Because it grows down, which means anything above this stack pointer must be in use by somebody, or could be in use by somebody. What about the stuff below the stack pointer?
Anything else?
Garbage. It could be anything. It could be any cruft or whatever was here on the stack. But fundamentally, the stuff here is not in use. So if you think about it in terms of memory usage, well, we're using everything here, but everything down here is free to use and take. Yeah.
Would be other like important program stuff below it, like that it could grow into, or?
Sure, but we'll ignore that. So there's, I guess technically yes, but the way it works is you'll hit a page fault or a seg fault before you reach anything else, so you probably won't. Yeah.
So when you add something to the stack,
Yes.
is this address less than or greater than stack?
Let's look, because this is the example. And I wouldn't say add it to the stack, I'd say push and pop. Yeah. Okay, but the important thing is everything below is garbage, right? Garbage memory, we don't know what it is. It could be literally anything. So let's say we just have an incredibly simple program, push EAX, pop EBP. From our intuition, what should be the result after these two instructions execute? Like what's the purpose, the semantics of these instructions?
They're opposite in theory.
So what should happen at the end?
So you'd think at the end that there would be no result.
We move the value into UTX.
So there's no result to ESP. So ESP is pushed and then popped, right? The stack pointer should remain at the same location after the fact. What about the registers?
Change EAX and EBX. So it'll push from EAX onto the stack and then pop that value into EBX.
So it's going to take the value from EAX, put it onto the stack, and then what's the next instruction going to do?
Push it into EBX or pop it.
Then pop that value into EBX. So then what does, so after all this executes, how does EAX change? It doesn't. How does EBX change? Yeah, now here's the value of EAX. So essentially we're copying from EAX into EBX using the stack. But let's look at how this works. So the only important registers here are EAX. Let's say it has the hex value A. EBX has the hex value 0. And ESP, we already said by this diagram, if I'm saying the stack pointer is pointing to 10,000 hex, it must have the value 10,000 hex. Good. Cool. All right, so we are currently about to execute this instruction. So we don't have an EIP, the instruction pointer here, but we can say that that points there. And so we say, okay, after this happens, what must happen? So a push EAX first decrements the ESP value by 4, pointing here, and then copies whatever's in EAX at that memory location. So the stack, so the ESP register will decrement by 4, FFFC, sorry. The stack pointer will move down, EAX will be copied there, and then now we've done everything of push EAX. So we've taken the value inside the EAX register, put it onto the stack, and now the stack has moved down 1, so now 1 more item is being used on the stack. Good? Questions? Yes.
The stack pointer always moves down.
Yes. That's why, I mean, you just have to remember where it moves. But yeah, so it's moving down. So pushing moves the stack pointer down,
Okay.
and popping moves it up.
And that's why everything above it is bigger, because it has to be above it.
Exactly, yes. So everything, exactly. Now EAX, this value is in use by the stack, right? So that value is in use and everything below it is garbage. Cool. So now when we do a pop EBX, now what we're going to do is we're going to fetch whatever's in memory address FFFC, and we're going to say copy whatever's there into EBX, because we're going to do pop EBX. And then because we're popping, we're going to add 4. So it's literally the exact opposite sequence of pushing, right? Push was decrement, then copy value. Pop is copy value, and then increment. So pop EBX copies whatever's here into EBX, which is now 0xa, and adds 4 to ESP, so now ESP points here. So now this value that's below 1000 is garbage, right? We know it has the value hex A, but we don't care because it's essentially garbage at this point. So, and did the execution that we just walked through here follow our understanding of what would happen to the registers here? Yeah, so we essentially copied from EAX into EBX. Why didn't the stack pointer change as a result of these 2 instructions?
Because they complement each other, the push and pop.
Yeah, we have equal numbers of pushes and pops, right? So because of that, the stack pointer will remain at the exact same location after that's all done. Questions on this? Yeah.
I'm sorry.
No, you're right.
A little bit. So, on the pop step, can you go through what happens?
Sure. Well, why don't you go through? So pop happens. What's the first thing that has to happen?
You gotta store the value at the top of this stack.
Yeah, where?
0xa.
Yes, where do you put it?
EBX.
EBX register, because that's the argument to the pop instruction.
Yeah.
So you're going to copy OX, so you're going to essentially dereference FFFC, dereference that, say whatever's there, copy that into EBX.
Oh, okay. So they're like, those are distinct.
Exactly.
What's actually inside the stack is different from what the stack pointer references.
Exactly.
Okay, that makes sense.
And then that's why then ESP, then you increment it by 4 in order to do the pop and moving the stack up 1. There you go. Any other questions? This is an important base concept that we're going to build on. Cool. All right. So now that we have that, we mentioned that we need some way for functions to use the stack in order to store their local variables. So it's actually, I think, slides I stole from when I used to teach 340, because that's the function frame is a core concept of both compilers and also for understanding buffer overflows. So we have functions that want to use the stack to allocate space for their local variables. So can we use the stack pointer for this? So let's say we just have to figure out, so like a function executes, and how do we map, so let's say there's a local variable integer a, how do we map that to a variable on the stack?
Just push it on the stack.
Yeah, maybe we could push it onto the stack, but then we need to, whenever we reference it, we need to figure out where we are from the stack pointer to reference that, like how much offset from the stack pointer we need. Yeah.
With the stacks, enough to have room for all the variables in the function, and then you can dereference it relative.
Yeah, so one option would be, let's say, so my function starts executing. I know I have 2 local variables, so I move the stack pointer down by 8 to allocate enough space for my 2 variables on the stack, and then I can use offsets of ESP in order to reference all those variables. But this gets a little bit tricky because as the function executes, the function itself can push values onto the stack for various reasons. So it's a little bit of a pain to do this. So the other notion is, well, how about each function sets up what they call a frame pointer or a base pointer, that every local variable is an offset of that base pointer. So this is actually, so everything is, on x86, there's a nice register called the base pointer, EBP. This specifies the base pointer of the currently executing function. This will make much more sense with an example. So let's say we write some code. So we have a main function. We have int A, int B, int C. How many local variables do we have?
3.
3, how much space do we need for those local variables?
Depending on the size of the two bits in the float. So we should be
4, how much size is an integer, an int?
4.
4 bytes? So 8, and then
So 16.
how much is a float?
Is it 8?
4 as well, I believe. A long is 8. And then a long is more. I don't know, it's a 30, 32 maybe? 6? Yeah. Let's look to make sure, but we'll see. The compiler will tell us. Then we have some code. So we have the declarations. And it's actually, well, anyways, we'll ignore that for now. But, okay, so then we just have some code that's doing stuff, right? We have our computation, set A equal to 10, set B equal to 100, set C equals to 10.45, A is equal to A plus B, return 0. Right? So this is what we give our compiler as input. Seems like a pretty simple function, right? Do some computation and then return from the function. So what has to happen? So the compiler needs to say, okay, for this main function, I have 3 local variables, so I know I will need space on the stack to store at least, what do we say, 12 bytes on the stack. And then I need to figure out on my stack, where is all the offsets for my local variables A, B, and C. For instance, it'll just say, hey, at EBP plus some offset A will be local variable A. At EBP plus some offset B, which is obviously should be different from A and not overlap, will be B. Then C will be at EBP plus C. And then at a conceptual level, all of this becomes essentially very easy. So using this, how would you compile this A is equal to 10?
Move 10 to the register, or is
A is not in a register. A is stored specifically. So this is the important thing, right? So the compiler will use registers to make things faster, but these are all local variables, meaning they need to be stored in memory on the stack. But you were saying something that I think was
Yeah, so yes, just push it onto the stack there.
so close, but specifically where on the stack? Yeah.
Where the offset is for A, you move a 10 into there.
Yeah, so move a 10 at EBP plus 10. So EBP has a memory pointer. We'll figure out how that gets set up earlier. But assuming it exists at the correct place on the stack for this function, we'll say we'll copy 10 into EBP plus A. Yeah.
Sorry, just probably a silly question. I thought you only had to store local variables on the stack if you made a function call to something else to kind of save your place for when you come back from the other function call. I thought that you would use normal assigned memory to the program while you're still in the same function.
What do you mean normal assigned memory to the function?
I thought that whenever you ran a program, you got an assigned section of memory for that program running that you requested.
Yes, so that would be global variables. So global variables get compiled to essentially a fixed location in memory, so they can be referenced by everyone else. Technically, the compiler could look at this and say, does the return of this function depend on any of this computation?
No.
No. So if you get rid of this and replace this with a function that does return 0, right? Technically. It can also realize, oh, I don't actually need to store anything on the stack. I can optimize these out into registers, but when you compile it specifically with no optimizations, it won't do any of those steps.
Okay.
Yeah.
Okay.
So that's why looking at compiler output is difficult, because it changes all the time as it's updating.
Yeah, I gotcha. Okay.
Why are we doing EBP plus A? Why not ESP?
So ESP can change throughout the execution of the function. So what makes this really nice is every place I see E here, I'm going to replace it with EBP plus A. So here's EBP plus A, EBP plus A, EBP plus A. If we use the stack pointer, we would have to keep track of if we stored any temporary variables, any temporary variables onto the stack. We'd have to figure that out and adjust for that when we reference A later. So x86 64, I think, can optimize away the use of the base pointer and just use the stack pointer, but that makes it more confusing. Yeah.
Why isn't it, would it be EBP minus A?
Well, I didn't say what A was. Yeah, just some offset right now. Yeah. It
So-
theoretically doesn't have to be a negative depending on how you set it up, but yeah.
For the, so like say like May was to call another function. and-
Yeah, we'll get there. Don't worry. Yeah,
This
yeah.
one.
Yeah, we're gonna get there. So you can compile these basically one-to-one. You can say, well, the memory of EBP plus A is equal to 10. So set the memory of EBP plus 10 equals plus A equals 10, and we just compile these line by line. B memory EBP plus B is equal to 100. Memory of EBP plus C is 10.45. Memory of EBP plus A is equal to mem of EBP plus A plus the memory of EBP plus B. Right? Just straight line, compiling one line to the other. Nothing super complicated here. And so looking at one compilation from this, let's say the compiler decided that A was at EBP minus C, B was at EBP minus 8, and C was at EBP minus 4. Right? We can, whatever, we can just say that. So then looking at the assembly instructions, we can then map these to these functions. So this is one time when I compiled this a while back. If you do this on your own, it will be slightly different depending on the compiler version. So we first have two instructions that we'll ignore for now, but essentially we can say that this subtract hex 10 from ESP is moving the stack down to creating room on the stack for our local variables. So, and essentially what we're doing here is moving the stack pointer into the base pointer. So the base pointer is where the stack currently is, and then we're moving the stack down by 16 bytes. And then in all these cases, so here we have our first A. So A was at EBP minus C. We're moving hex 10 into EBP minus C. Right? We're then moving 64, hex 64 into EBP minus 8. Hex 64 is 100. I mean, I'm fairly confident I didn't memorize that, but based on this example. And then we're moving hex 41273333 into EAX. What is that value?
It's like 110.45.
What was it?
Is it 110.45?
Yeah, it's not 110, but 10.45 in IEEE floating point format. So, but it's not stored in memory yet. We need to actually store that in memory. So we need there's another instruction to move EAX into EBP minus 4. Yeah.
Quick question, so is EBP always going to be used for the function frame? Or like, could it be overwritten?
In most cases, yes. So when you're looking at assembly code, it's used to define the function frame.
Okay.
Yeah. I mean, technically code can do whatever it wants.
Yeah.
But the convention is when you look at what we're going to be looking at, x86, 32-bit Linux systems, they will use that. Yeah.
So are you altering memory on the stack without changing the stack pointer and pushing and popping? EBP is pointing somewhere on the stack, right?
Yes, we're going to go through a visualization of this and walk through exactly these statements. So that should help clear that up. Then we need to do the compute. So now we've done up to here, right? So at the end of these instructions, EBP minus C will have the value 10. EBP minus 8 will have the value 100. And EBP minus 4 will have the floating point, IEEE floating point of 10.45. Yeah.
For floats, why can't you move it amongst that?
Yeah, so this is a, if I remember correctly, the x86 32-bit instruction format. You can't move, like, this value, literal, that you're moving here can't be a full 32 bits. So here's a full 32-bit number, and you can't express that to move that here, so I believe you need to use extra steps. Yeah, I don't know. The default answer is usually because the compiler did it that way. It's sometimes difficult to divine why. Yeah.
Why aren't push commands used directly and instead we're removing and subtracting instructions?
Yeah, we'll see that in a second. Again, I think it's efficiency. So instead of pushing, because here, so if you think, so this is 16, so you need 4 pushes in order to change the stack pointer to where you wanted it to be. Local variables could be, when you have a buffer that's a local variable, that could be 512 bytes. I mean, it could be a huge value, so this value moves the stack pointer down in an efficient way without pushes and pops. Yeah.
Wait, so what was the point of subtracting from BSD?
Yeah, we're going to get to that. We'll see that in a second. Okay, let's look finally at the last bits of computation. Move. Oh, yeah, so move EBP minus 8 into EAX. So now we need to get the values from memory to perform computation in registers. So here we have EBP minus 8, which looking at this handy chart is B, moving that into EAX. We're going to add EAX, which is B, to EBP minus C and store the result in EBP minus C. So here we've done A is equal to A plus B, because we put B in the EAX register, and A is at EBP minus C. And then there's other stuff, but we'll ignore that for now. So let's look at what's going on here. So here's the code. Now here's our handy dandy stack. Let's say again the stack is pointing at 10,000. Nice thing here is that we only need EAX, ESP, and EBP. So there's only 3 registers we care about. Now, which of these registers do we absolutely know the value of? ESP. Why ESP?
Because it's only 1,000 or 10,000.
Right, because this pointer here, I just said it's 10,000, right? So we don't know exactly what that value is, but we can say it's there. So, and before this code executes, we don't know what's inside EAX, we don't know what's inside EBP, we don't know what's above on the stack, and we don't know what's below the stack, right? Just somebody called this function. All right. So what's the first thing? So what's this instruction at the top going to do?
Copy ESP into EBP.
Copy ESP into EBP. So EBP will now point to 10,000 hex. And then what about this line?
Stack pointer down.
Yeah, it's going to move the stack pointer. Does this affect the base pointer?
No.
No, right? Because they both have the same memory address, but here we're only operating on the ESP register. So we're going to move down 4 of these values, right? We're going to subtract 16. So now I have 2 pointers. So what are these 2 pointers? EBP and ESP, right? And I know them because they're in these registers here, right? There's just a visualization of where these point to. So essentially, now looking at this, what did this subtraction do for us?
It gave us space to work with.
It gave us space to work with that is in use by the stack and nobody will mess with, right? Because we know now the stack pointer points down here, everything above that stack pointer is in use by the program and nobody else will mess with it.
So what I'm confused about isn't the interaction on its own, but when it interacts with other programs. So say like the program below it pops out all its stuff and is done with it.
You mean programs or functions?
A function
Because
is a totally different program.
different programs are in different memory spaces. They can't mess with each other's memory.
Okay, so they each have their own stack.
Yes.
Okay, that's why.
Yes. Every process, every program has its own stack. You get into threading later, that gets slightly more complicated, but essentially all this code will have access to its own stack.
Okay.
Cool. All right. So then we just walk through these steps. So now, EBP minus C, we know it's exactly, so this is EBP, EBP minus 4, EBP minus 8, EBP minus C. So we know that this move 10 into EBP minus C will move 10 here onto the stack, right? So essentially our local variable A just got set to the value 10. Then move 64 into EBP minus 8 will move 64 here onto the stack, EBP minus 8. And then these 2 operations, moving that floating point value into EAX, and then moving EAX into EBP minus 4 puts that there onto the stack. I don't know what that, oh. So essentially, you can see on the stack, we have the variables A, B, and C laid out onto the stack. Why did the compiler decide to put them in this order? Yeah, no, I don't know. Don't be fooled by patterns. I don't know, weird stuff happens, yeah.
So my understanding is that like they allocate as much space in the stack from the local variables you have. So why is there 4 extra?
Yeah, it is, again, a compiler. It's actually, I think, an optimization per weird architectures. So some architectures, your stack pointers have to be, I think, 4-byte aligned or something like that. And so in these cases, they'll always allocate to that space. But yeah, there's some crazy GCC forum thread about this. Like, I don't know, compiler stuff is the real answer. Yeah.
I'm gonna try to group by variable type though, to put it on.
No, I don't know. Yes, sometimes, maybe, depending on the compiler. Kind of. It's difficult to get into. Really, I mean, the real thing is, and this is why we're looking at specifically this is why looking at the compiled binary output is so important, because this is what actually happens, right? That C code of A, B, and C is essentially a fiction as to what is actually going on. But yes, I'm sure compilers do all kinds of weird stuff. Yeah.
So you said that every program has its own stack. Is that the same for heaps? Or do they all?
Yes, their own memory space. So each program thinks they have exclusive access to all, in this case, a 32-bit 0 to 2 to the 32 memory. So you have to explicitly enable memory sharing between programs. But yeah, that's, yeah.
So after mom L0x64, which that makes sense to me. 100 is where T is stored. There's a step after that. And I think I missed it because the arrow is always down.
This one?
Yeah. No, where am I? Yeah. Well, let's talk on that.
So we're moving, so what's this value? 4127333333? You tell me, what is that? What must it be? So what was?
Probably the 10.45.
Yeah, so it's 10.45 and IEEE floating point, right? I don't know that, it's just deduction, right? So we can see 10, we can see 100. This is the only other value in the program. So if the compiler decided the best way to move this value into EBP -4 is through EAX. So those two instructions, the first instruction copies that value into EAX, and that second instruction here copies that value onto the stack.
And then EAX is.
Just a register that's using.
Oh, sorry.
Yeah.
So only the bottom two of those three registers are one that has a convention to it?
Yes.
Okay.
Yeah. EAX, EBX, ECX, EDX, they're general purpose registers. They also do have some important values later that we'll talk about. Return values are put into EAX, but we can ignore that for now. But yeah, there's some conventions, sometimes, let's say.
Why did you say APP?
Because, next question. Say it again? So you can't, I believe, based on the x86 syntax, you can't move so this value is 32 bits, right? It takes 32 bits to describe this value. You can't move a 32-bit immediate value into a memory location. I think that's too long of an instruction. It doesn't, you can only move an immediate into a 32-bit immediate into a register. Whereas these other instructions are smaller, so it only needs to encode that byte and says move this into EBX -C. Yeah, it'd be much easier. I mean, it'd be more clear like that, but cool. Okay, and then now we perform our computation. So now we're going to move EAX into EBP -8. So now EAX has the value 64, which is what variable name in our C code? What was it? B, right? So moving B into EAX, and then adding EAX to whatever's at EBP -C and storing the result into EBP -C. So EBP -C is here, A on the stack, so we're adding 64 to hex A, and we will get hex 6E, which should be 110, and then we're done. Good? Questions? Yeah.
So in assembly, does it automatically add the two values and store it in the first, or sorry, would be the first or the second?
Yeah, so an add instruction means add this value and store it in the last value. Yeah, so there's an implicit destination in there. I believe that's consistent with all, or most. Anything else? Gonna ramp up. Okay. So we saw how this allows us to allocate space and memory for the function's local variables, but when we want to call another function what do we need? So think about, you're writing a function to call a function. What information do you need to call a function? Yeah.
Where that function is located.
So the address of that function, yeah, where that function's located, what else?
Where you came from.
Where you came from, you need to know how to go back after that function's executed. What else?
Your local variables before their values.
You need, well, you want your local variables to remain the same after you call a function, right? If that function changed your local variables, that would be bad. What else?
What you're passing to it.
Yeah, the parameters that you're passing to the function. What else?
When you get back its return value.
Yeah, you need the return value from the function, right? Oftentimes you call a function, you want to see what it returns. Awesome. So we need return value parameters, and we want to call a function and have everything be exactly where we left it, right? We don't want a function to come in and move stuff around. So we need things like, well, we'll go into this. Anyways, what we need is some kind of calling convention, because we need to understand, okay, who does what? So when I'm calling a function, do I have to save my base pointer, or do I expect the function that I call to do my base point, like save my base pointer for me, right? So, and where does the function put the return value, right? Because it's easy when we're programming, we say int a equals function foo, right? But as we saw, it's all assembly. So where does that return value go when the function returns? Who deals with this return address of where to go back when this function's done executing? So we need some kind of convention. And this is one of these things that varies based on the processor architecture, the OS, the compiler, or specifically the type of system call. So even on, right now we're going to focus on Linux, x86, 32-bit, but still there's different system call conventions, there's different calling conventions if you're calling a function versus a system call to the operating system. And we looked at those briefly with looking at system calls from assembly. But we can ignore that. So we will be looking at cdecl. This is the calling convention we will focus on. So before calling a function, the caller of the function first pushes all the arguments to the function on the stack in a right to left order in terms of parameters. Right? So you think calling a function, you have A, B, C. So before calling the function, you first push C onto the stack, and then B, and then A. Then the caller is the one who has to then leave the address of the instruction after the call. We'll get into this more in a second. Oh, sorry. And that's all that they need to do. So that's all that the caller needs to do. The callee is responsible for everything else. So the callee is responsible for saving the previous frame pointer. So it needs to save the frame pointer before it uses it. It then needs to create space on the stack for local variables, which is what we saw. And then ensures that the stack is consistent when it returns, so it doesn't return with a weird different stack. And then finally, the return value needs to be put into the EAX register. So this is another instance of a register having a special value in the context of calling a function. This also means that the compiler, that when we call a function, we can't expect whatever was in EAX to remain the same. So there's other semantics here about what functions can use or have to save what registers before they use them, but we can ignore that now. It doesn't really matter for what we're talking about here. Okay, we should probably look at an example of this because this will make a lot more sense. So we have a very simple function, main, int a, local variable a. It's gonna call a function called callee, pass in 10 and 24, set that value to be whatever the return value is to be a, and return a. Callee is a simple function that takes in two integer parameters, a and b, and returns an integer and just returns a plus b plus 1. Pretty simple program and function. Okay, so let's walk through the exact, so now we're going to look at the exact assembly output of these functions, so how they actually got compiled. So here's the function main. The function main, now, is main special as a function?
It's the entry point.
Yes, in the sense of what?
That's where the program starts.
Yeah, it's where the program starts, but is it special in any other aspect? No, so it needs to actually go through these steps as if it was called by somebody. So it needs to store the previous frame pointer on the stack. It needs to create space on the stack for its local variables. It needs to ensure that the stack is consistent on its return, and it needs to put the return value in the EAX register. So this is an important thing. I used to have a crazy code on a 340, maybe it was an exam or something, where main would like call itself multiple times as the program executes. Just to reiterate the fact that like main is not a special function at all. So first thing it needs to do, it needs to save the previous base pointer because it got called from somewhere. We don't know where. It needs to store that function's base pointer. Then it needs to create space for its stack. So it's going to first set up its base pointer by moving the stack pointer into the base pointer. This is exactly the same as what we saw before. Then it's going to subtract 18 from the stack pointer. Why 18 in hex? Which is what, 32? How much local space does this function need? How many local variables are there? One. What's the size of those variables? 4 bytes. Why does it need 32 bytes? Yeah.
Are you making room for the argument killer?
Yeah, so it's like optimizing space for the arguments. Instead of actually pushing the arguments on, we'll see that it pre-allocates space. But all right, so let's look at the next. So we first move hex 28 into ESP plus 4. So plus is going to be which direction of the stack? So stack pointer
Up, down.
up. Down is negative, so plus 4 is up into memory that is allocated memory. So we're going to move hex 28. What's hex 28? 40. Well, it must be 40. It's not 10. Right? 10 is A, so it must be 40. So moving that into ESP plus 4, moving 0 at where ESP points to. So now we've actually set up the stack with all the parameters that are required for this call. We've pushed onto the stack from right to left, 40 and then 10. And then we're going to call this function. And that's all we need to do to call a function. Then what do we do with this return value? Where do we get this return value from? EAX, yeah, so we can just move whatever's in EAX into EBP minus 4. What's EBP minus 4 here? A, yeah, it's just where the compiler decided to put the local variable A. And you'll see the compiler does some stupid things because it's doing this just to be correct. It's not trying to optimize. So it does things like move EBP minus 4 into A. Why is this silly? Yeah, it was already there. It literally moved it from EAX into EBP minus 4 and then EBP minus 4 into A. And then we'll have 2 instructions that we'll see that are important. We're going to do the leave instruction and then a return instruction. So, yeah.
Why does EAX get to move 4 down from the base pointer?
That is just where the compiler decided to put the local variable A. So int A here is a local variable.
Oh, yeah.
The compiler just decides it's at EBP minus 4. Okay, important things when looking at this function. What does this function actually do? So looking at the actual meat of this function, what does it do?
Outputs a constant number.
Technically, yes, but what does this program actually do? Like this function.
Adds together and plus 1.
No, just looking at main in isolation, not looking at the whole thing.
Calls another function that returns
It calls another function by passing it the parameters 10 and 4, and then returns that value, right? So, in here, really the code that gets called is essentially in here, right? So this is setting up 40, 10, calling the function, and then setting up the return parameter, and the return value. And so it's important to understand and look at every function has this prologue that essentially sets up as we saw, what a function that gets called has to do. It has to store its base pointer. It has to set up local space for its variables. Okay, and then in the epilogue, when it leaves, it needs to go back to where it came from and needs to make sure the stack is consistent. Right, so we'll see exactly what those do. You can essentially think of it as leave and return. Leave is essentially the exact opposite of these 3 instructions. So callee is much is simple, right? All it does is take its parameters a, b, add 1 to them, and return. Does it have any local variables? Nope. So callee has to store its caller's base pointer. So it pushes its base pointer onto the stack. It moves the current stack pointer into the base pointer. It then moves EBP plus C into EAX. It moves EBP plus 8 into EDX. It then adds 1 to them. So this is a weird, this load effective address takes EAX plus EDX plus 1 and moves it into EAX. I don't know why the compiler decided to do that. It just did. Oh, no, sorry. The 1 doesn't happen from here. The 1 happens here. That's right. Add 1 to EAX, pop EBX, and then return. So again, callee itself has a prologue and epilogue. It's slightly different just because it's not it doesn't have this subtraction step. So it doesn't have any local variables here. So what's this EBP plus C and EBP plus 8 here?
That's where the parameters are stored in memory, right?
Yeah, that's where, so the base pointer, as we'll see, when a function gets called is, so we saw everything negative from that base pointer is local variables. Everything positive from that base pointer is all parameters. There we go. So those are the parameters that gets passed in. We'll see exactly why that works. We can think of it as the opposite of here. So here we're moving them onto the stack. We call the function. The function picks them up by going offsets of the stack. Yeah.
Why does main have to use the call function?
Because the callee doesn't have this subtraction here. So the compiler decided that it would be simpler to just do those 2 instructions. Okay, let's step through this code. So we have our 2 functions, leave, callee, and now we're going to get even more crazy. We're going to give each of these assembly instructions an address. Remember, it's important to remember that these are just bytes in memory at certain memory addresses, right? And the compiler, the CPU is very stupid. It essentially starts executing at 804, 83, 85, does the next thing, and just keeps going until it needs to move or change or do whatever. So we have our nice handy dandy stack, and now we have our registers. We're using slightly more registers than before, but actually not that much more. So we use EDX somewhere, and EIP will be the instruction pointer. So this will be the pointer to the next instruction that needs to execute. And we'll say the stack is up top when I ran this, and this is actual output from debugging this from when I ran this, like the memory locations and everything. So FD2D4 will be the stack pointer. Cool. Do we know what's in the base pointer? Or any other registers, do we know? We know 1, or we should know 1, let's see. Yeah, we know 1 is the instruction pointer. So the instruction pointer is 804, 83, 85. That means that's the next instruction to be executed. Now, is there anything special about what's going on? No, it's all just the semantics of what these instruction means, how it operates memory, how the stack moves, how the registers move, right? So just going through them and demonstrating what happens here based on what happens here. So again, why do we do push EBP? Yeah. Yeah, somebody called us. It's that function's base pointer. We need to save it so that when we return to them, we can restore that base pointer. So we don't know what it is. It has some value. Let's say it's FD2C0. So when we do push EBP now, so the stack pointer moves down. So the stack pointer moved to FD2D0. And we moved FD2C0 onto the stack, which was the previous base pointer. Good. So hopefully, if everything works right, by the time main leaves, when it returns to wherever it came from, the base pointer will be FD2C0. Good? Now we need to set up our function frame, which we looked at. We move the stack pointer into the base pointer. So now the stack pointer points to FD2D0. So the stack pointer, base pointer now point to the same thing. We're going to allocate space for our local variables. We're going to subtract hex 18 from the stack pointer, moving the stack pointer down here. The base pointer doesn't change because the base pointer, we need that for offsets of our local variables. Good. Yeah.
How did the base pointer get FD2D0 versus FD2D4 originally? When did we move down to 4?
By pushing EBP, we subtracted 4 from the stack pointer.
Okay.
So at this point, the ESP has FD2D0 because it moved down 1. You can debug backwards in this. Go forwards and backwards through time. No? Okay. All right, so next up, now we're going to get ready to call this function. So we move the hex value 28, which is 40, into ESP plus 4. So ESP is at FD2B8. 4 above that is this memory region here. So we move that there. We then move hex A into ESP. And now we've essentially pushed onto the stack right before we call this function. We've pushed 40 and then 10 onto the stack. So we've done our share for calling a function. We had to push all the parameters to the function on the stack from right to left order so that the function can find them. Questions on this? Okay. Now we want to call this function. And again, we don't really know it's a function. All we know is it's some memory address, 804.8394. Start executing at 804.8394. But we need to be able to go back. So specifically, in this example, what address do we want to be executed after this call is returned? 3BF, specifically this instruction right here, 804.83BF. How does the function that we call, how are they supposed to know that that's where they need to go? The base pointer is FD2D0. Yeah, fundamentally, so think about this. Remember, functions can be called from anywhere. So a function doesn't necessarily know all the places it can be called from. So essentially, how many people know I'm not going to go into it in detail, but the story of Hansel and Gretel? Right? So they leave the house and they leave a trail of bread crumbs in the forest as they go into the forest. So to find their way back home, they follow those breadcrumbs. So we need something similar. We need a breadcrumb that lets us know how do we go back to the function that called us. And that is exactly what this call instruction does. So the semantics of this call instruction do 2 things. One thing says start execute, essentially change EIP to be 804.8394 because that's the next instruction to execute. What it also does is it says push 804.83BF onto the stack. Specifically this because it's the next instruction after the call instruction. So what the stack looks like after this is we've stored onto the stack 804.83BF. This is our breadcrumb so that the callee function knows where to go after it's executed. Yeah.
So wait, did we lose the original instruction pointer that called main?
Mm-hmm. Yeah, EIP is now 804.8394. So if we just had if this was a jump, 804.8394, we'd have no way of knowing where we came from. That's why we have to build in this mechanism of these breadcrumbs of how to go backwards. And that's by saving the instruction pointer onto the stack.
And is that one that's currently on the stack, the one that called main?
We haven't looked at that, but technically, if we worked this backwards, we would see right above FD2D4, or actually right at that memory address, would be the return address for main.
Okay.
Yeah. Cool. Now callee is executing. It has no idea who called it or what the environment is, right? Just like when we looked at main, we had no idea who called it. And so the first thing main needs to do is store the base pointer of the person who called it. So callee is going to do push EBP, and then it's going to move the stack pointer to the base pointer, creating their own base pointer. So now we've basically gotten rid of everything from main. We don't know where main is, but we've stored on the stack enough information to be able to go back to main and set the entire environment up so that main can start executing. Good? Questions? Yeah.
How does, I think I missed it, but how does BF appear on the stack again?
The call instruction.
Okay.
So the call instruction does two things: sets EIP to this value or wherever it's supposed to go, and pushes this address of the next instruction after it onto the stack. So it's like a two-parter. So now calling needs to do its computation, right? It's done the prologue, it's set up its function frame. Now we can answer this question. What is EBP plus C? So specifically, let's walk through this. So what is at EBP?
Base pointer for.
The saved base pointer. Yeah, whoever calls us base pointer. So we'll call it the saved base pointer. And then what's at EBP plus 4?
The next instruction main.
Yeah, so the saved instruction pointer, right, of whoever called us. Right? So saved base pointer, saved instruction pointer, and then what's at EBP plus 8?
The first parameter.
The first parameter, right? The leftmost parameter, the first parameter to the function, is at EBP plus 8, and then what's at EBP plus 12?
Second parameter.
The second parameter. So when we look at this code, we see, oh, EBP plus C into EAX. It's moving the second parameter, which I think was B, into EAX. Right? And because of the calling convention, this function callee knows that the arguments to the function, the first argument will always be at EBP plus 8, and the second argument will always be at EBP plus 12. And it can guarantee that because it knows that if anybody wants to call it, they have to push their return address onto the stack, and they need to, and callee itself stores the saved base pointer, the base pointer onto the stack. So this has to be true based on the calling convention. Okay, questions? Cool, so let's walk through this computation. It was just add the two parameters together and then add one. So we're gonna move EBP plus C into EAX. Oh, yeah, so before we do that, now looking at the function frame, we can essentially see that this function frame belongs to callee and that function frame belongs to main. But going forward, so we move 28 into EAX, so EBP plus C, which is here, move 28 into EAX, moved EBP plus 8 into EDX, add them together and put the result into EAX. So EAX now has hex 32. Add 1 to EAX. And what were we returning from this function? Yeah, return A plus B plus 1. Based on the calling convention, where do we place the return value? In EAX. What's the value in EAX? A plus B plus 1. Right, so we've added our two parameters together and added 1 to them. Now we need to do this whole thing in reverse. Right, so now we need to, so what's this pop EBP going to do? Yeah, so take whatever's currently on the stack, and remember we know that currently the stack pointer right now is pointing to the saved base pointer. So by doing a pop EBP, we're going to put this value back in here. Whose base pointer is this? Main's base pointer. So we're going to restore main's base pointer. We do a pop EBP. So now main's base pointer is restored. And then now we need to do a ret. So a ret is the opposite of a call instruction. What did a call instruction do? Changes EIP and close. Yeah, the next address. So changes the instruction pointer to call the function and also pushes the saved return address onto the stack. Now we need to do the opposite. We need to go execute. So essentially you can think of a return as a pop EIP. Because what are we doing? We're taking this address, we're going to move it into EIP, and we're just going to start executing there, and the stack's going to move up. So pop EIP. How does the CPU at this point know that this is where main wants us to go?
It was there before, we just assume that that's from me, wherever the last one.
Yeah. The call function had saved that EIP on there, but how does it know it's exactly this value? Sure, it's done symmetric operations, but how does it know that this value hasn't been changed since we called this function? It doesn't. It's dumb. CPUs are dumb. They don't do checks like this unless it's in the code, right? This code, all it does, this return function says, whatever 32-bit value is here, I will start executing from. In this case, it's going to go start executing here at BF and continue execution. So what I want you to be thinking about as we continue this is, what if as an attacker we can control and overwrite that value? Yeah. Technically, yes, sure. Yeah. But that would be more like, the question, that would have to be in the code itself, not necessarily the CPU doesn't magically know that this value is correct. Yeah.
So when we disassemble a function, we're seeing the instruction memory addresses?
Yep. Those addresses?
Yeah.
Yes. I mean, for all the, unless there may be position independent executable in which set their offsets, but you can just debug the program, break on main, and you'll see the actual literal memory values. Yeah.
I remember initially EIP included the value of the call lead function where we started that.
Mm-hmm.
When did it become QGF?
This one?
Yeah, that was the initial value of EIP. That was the first jump of call lead, right?
Yes.
So then how did it become BF?
So the call instruction itself pushes it sets EIP to this value and pushes onto the stack the address of the next function. The call instruction itself, you can think of it, it knows how big it is, so it can tell you exactly where to go afterwards. Yeah. So then from this return, so this return is just pop EIP. Now we're here, we've changed our EIP, and from main's perspective, what happened? Not nothing, close.
EAX changed.
EAX changed, right? But nothing else did. The stack is still exactly where we left it, right? We can see that there's other values that got pushed here, but do we care about those values? Why not? They're garbage. They're all crap that's after the stack pointer, right? So it's not part of the stack, it's not part of allocated memory, it's garbage memory. We don't care what those values are. But we got our return result in EAX, and that's what we wanted. So now we're going to use that. We're going to do these two silly operations. We're going to move EAX into EBP minus 4, and then move EBP minus 4 into EAX. Where now we need our epilogue, so now we need to do the same thing that Kali did of set the stack exactly where it should be. So a leave instruction does two things. So we have our base pointer and our stack pointer. So a leave instruction says set the stack pointer to be the base pointer. So what happens to my 2 pointers then? So the stack pointer moves up, right? So base pointer's up top, stack pointer's down here. Leave says move the stack pointer, move the base pointer into the stack pointer, so it points up here, and then do a pop EBP. So it does two things. It gets rid of all of this allocated space so that no matter how much we subtracted from here, we'll get rid of all of it, move the stack pointer to where the base pointer currently is, and then do a pop EBP to set and restore our saved base pointer. Yeah?
Is there a reason we didn't do EVA calling instead of pop?
Yes, because call E doesn't subtract from the stack pointer, so the compiler knows that it's pointing at exactly the same place as EBP, and I think based on space, a pop EBP is less instructions than a leave, but I'm not 100% certain on that. But anyways, the compiler decided to. So here we have our leave. So the first thing that gets done is the stack pointer and the base pointer get set to the same value. Then we pop whatever the value that was there into the base pointer. So now the base pointer is FD2C0. And where are we going to go execute?
At that instruction.
Yeah, whatever's at FD2D4, whoever called main. And just keeps going like that. So all function calls all operate on this basic philosophy. Questions? Yeah.
But if call E, when you access the two arguments,
Yes.
I didn't realize that you could access memory from the stack without popping. Can you?
Yes, because it's just a memory offset. So pushing and popping values on the stack change the stack itself. So when you want to do that, you can use that. You can just like subtract 18 from the stack pointer to allocate space onto the stack. You can just use the stack pointer, or here we're using the base pointer just as an offset, right? So to get values onto and off of the stack, similar to exactly what's happening, I think here is what we're talking about, of like ESP +4 and ESP. Okay, so for stack overflows, this was all background to get us to the point where we can understand what's going on with a stack overflow. The idea is if we are copying data without doing any bounds checking, oftentimes, did anybody, well, I'm sure this happened. So on, what was it, assignment 1, the secure house assignment, one of the inputs was incredibly large, so you couldn't pre-allocate in advance the space necessary. That was specifically to trigger like bugs like this. So normally, if you overwrite part of a buffer, you'll end up writing to unmapped memory. There'll be a seg fault. You've seen this in assignment 2 where you found seg faults in each other's codes. But as attackers, oftentimes we don't just necessarily want to cause a seg fault. We want to take over the execution of a program. So what if we overwrite the return address to something we choose as attackers? It's possible, I don't think we're going to get into shellcode. I think I skipped that. We'll see. But it's possible to then jump to code that you as a user define as the attacker. And fundamentally, now this code that executes will be executed with the privileges of the application. So again, this is reiterating what we just talked about. Save EBP and save EIP are stored onto the stack. And fundamentally, nothing prevents a program from modifying those values, right? You're an application. We said you have full access to your whole memory space. You are free to read and write to more or less all memory spaces in that program. So the question is, what if they did do that? So I will briefly go through this so you can do this on your own time. So we just have a function that copies a string onto a local variable on the stack. So this is a string you can pass in, my copy, that will copy that string pointer from there onto foo. Looking at this, we have a very basic function call. So here we have pointers to memory addresses. I just want to run through this so you can check it out on your own. I'm bumping it against the clock. All right, well, our next class on Tuesday will be pretty intense too, so study up.